Okay. Seats. It's my pleasure to introduce CP, who will tell us about parametricity via cohesion. Thank you very much. Yes, as the title suggests, this talk is about parametricity via cohesion. And if you don't know what any of those words are, don't worry, I'm going to tell you in a minute. Starting with parametricity, which is probably something that a lot of you have already heard about, but just to make sure we're all on the same page. So in 1983, John Reynolds introduced the idea of parametricity as a formal specification of his idea that type structure is a syntactic discipline for enforcing levels of abstraction. And what that means, roughly, is that in a system like polymorphic lambda calculus, or system F, a function with this type here can't inspect the types over which it's defined. And so it has to behave basically the same for all the types X that you can plug in here. And so, for instance, based on this, Reynolds was able to prove that actually all closed terms of this type in system F are equivalent to the polymorphic identity function. Like, you can't write anything else. And so Reynolds' original analysis of parametricity was wholly external to the internal logic of system F. But now that we have dependent type theory on the scene, this raises the possibility of doing parametricity analysis internally in the type theory itself in its internal logic. And so in recent years, there have been several attempts at coming up with various systems of dependent type theory that have some form of internal parametricity, but they've all used sort of different means to do this. And importantly, these have been applied in some really interesting applications in like homotopy type theory, in getting around some of the issues with like higher dimensional coherence. So this is a really kind of interesting thing to look into further. But like I said, as yet, there's sort of no unifying framework for all these different approaches to internal parametricity. And so this work is basically what I hope can be kind of a first step toward such a sort of unifying framework. And the key idea here is the category theoretic concept of cohesion introduced by Lavier. And so according to Lavier, cohesion is an abstract characterization of when one category behaves like a category of spaces defined over another. And what that means in particular is that we say that a topos is cohesive over another topos if there's a string of adjoint functors between them like this, where delta and nabla are both fully faithful and pi preserves finite products. And this induces a string of adjoint endofunctors on E, where the esh and sharp are both idempotent monads, and flat is an idempotent comonad. And so to give an example of cohesion like this, the category of reflexive graphs is cohesive over the category of sets. And the way that works is, so your gamma functor maps a reflexive graph down to its set of vertices, and pi maps the graph to its set of weakly connected components, like so here. So anytime there's a path between two vertices, they end up in the same component of pi. And then similarly, if you have a set, delta takes that set to the discrete graph on that set of vertices, and nabla takes it to the co-discrete or complete graph on those set of vertices. So you can see like it maps this set of 5 points to this K5 over here. And one important thing to note at this point is that many classical models of parametricity are based on models in reflexive graphs. And one thing I want to argue is that this isn't really an accident, and the main thing at play here is precisely the cohesive structure of reflexive graphs. But another thing to note is that actually for any base topos, the corresponding topos of internal reflexive graphs in that topos is also cohesive over that topos. So we can actually use the internal language of reflexive graphs to derive parametricity results for any topos. And going even a little bit further, the same idea of cohesion can be interpreted mutatis mutandis in infinity toposes in addition to regular toposes. And so that means we can use homotopy type theory to start talking about the internal languages of some of these. And so, okay, so I'm gonna quickly show you a bit what that sort of internal language looks like. And this is based on Mike Schulman's paper on cohesive homotopy type theory. And so when you start trying to include those modalities we saw that you get from cohesion, we face an immediate problem, which is that the flat modality isn't especially well behaved in normal type theory because it's not well defined in arbitrary contexts. It's only really well defined when the context consists entirely of variables whose types are also discrete. And so the solution to this is to modify the structure of contexts of variables in our type theory to keep track of which variables are discrete. And so what that looks like is that now we have contexts that are split between sort of normal and discrete variables. And you can use each variable in the same way, but when you go to extend a context with a discrete variable, its type has to depend only on other discrete variables in the context. And so that's how we can enforce this friction. And so then once you have that set up, the rules for your flat modality are very simple. If you've seen Fenning-Davies style accounts of modal type theory before, it's basically exactly that. And so basically you just get this type that internalizes when you have something that depends only on discrete variables and lets you pattern match on things like that to get those. And from that, we get this co-unit operation here that takes the flat modality of a type back to the original type. And we say that S is discrete if this co-unit map is an equivalence. And so now you might be asking yourself, how is this all related to parametricity? So cohesion lets us consider sort of the geometry of parametricity in a particular way. And so we can think of a type that classifies the shape of sort of parametric relations between elements of a type so that this type, if we call it I, functions out of that type should correspond to abstract relations or paths between elements of this type S. And so to give a concrete example of that, in reflexive graphs, this I you can think of as just the sort of walking edge graph that just has a single directed edge between two vertices. And there's two key properties of that. So it's strictly bipointed. It has two points that are provably distinct in the internal language of the topos. And it's connected. So if you look at its set of connected components, it's just one. So when you're just looking at connected components, this thing all gets contracted down to a single point. And so the existence of an object with these two properties was actually already considered by Laubier, who described an equivalent property, which he called sufficient cohesion. And so one thing that immediately follows from that is that in the internal language of a sufficiently cohesive topos, all paths in discrete types are constant. And the proof of that's very straightforward. If you have a function from this interval type to S, then since S is discrete, it factors through flat S. And then since the shape modality is adjoint to the flat modality, it follows that you can get a function like this that completes this square. And then since I is connected, this here is equivalent to just the unit type. And so that means that F factors through the unit type, and so it must be constant. And so one way you can think about this is that that means we have the discrete types in a sufficiently cohesive topos form a sort of sub-universe of types that have to behave uniformly with respect to parametrically related things, because they can't detect the difference between things lying in the same connected component. And so we're going to use this idea to sort of internalize the idea of parametricity. And so first we need some language for representing paths. And so to do that, we're going to borrow some ideas from cubical type theory and simplicial type theory. And so we postulate an abstract interval type with 2 points, 0 and 1. And then given a family of types that may depend on I, a path from a one element to another, S0 to S1, is a function out of I to S of I, such that satisfies this boundary condition, so that it evaluates 0 to S0 and it evaluates 1 to S1. And we write path sub S, S0 to S1 for the type of such paths. And we say that a type is path discrete if for all points in that type, the canonical map that takes proof that S0 equals S1 to a path between them is an equivalence. And the above lemma we had just says that if a type is discrete, then it's path discrete. And then finally, to make use of the structure of sufficient cohesion, we also need some way to make use of the fact that I is strictly bipointed. And so for this, we introduce what I call graph types. And a graph type, basically the way you should think of it is it's just a pair type where the second element of the pair only exists under the assumption that some element I of the interval is equal to 1. And so that means in the case where I is equal to 0, that assumption that I is equal to 1 is false. And so the type of the second element just collapses down to 1. And so then the graph type itself just reduces to the type of the first element. And so we strengthen this equivalence into judgmental equalities. And that's justified by univalence if you want to be picky about it. But so then finally, once we have all that set up, we can use it to start proving some internal parametricity theorems. And so let's go back to the classic old chestnut of the polymorphic identity function. So if we have a type, an element alpha of this type, and then for any path discrete type A, together with some type family depending on it, and a type, and an element of that type and an element of that family, then we can show that this is inhabited, i.e. any property that A has applying alpha at big A to little a has to also have that property, which is then going to imply the usual parametricity result that alpha has to be equivalent to the polymorphic identity function. And so I'm going to show you how to prove this in 3 easy steps using what we've set up. So step 1, you just define a function from the interval to this graph type, which has the key property that when you evaluate it at 0, it just gives you back this thing that we want here, this alpha applied at big A and little a. And you can do that by just defining this map here. And then when you take the second projection of that map, you get an element of B at some element of A, but it doesn't look like the one we're looking for, this alpha A of A, but that's okay, because if you take the first projection of step 1 just evaluated at an arbitrary element of the interval, that actually gives you a path from alpha, from the thing we do want to the thing that's showing up here. And since by assumption A is path discrete, that actually yields an identity between these two terms, and we can transport the thing we had in step 2 to get the desired inhabitant of this thing, and that completes the proof. And so this turns out to be a really powerful technique. You can use it to prove way more than just kind of toy results about the polymorphic identity function. For instance, you can use it to derive induction principles for inductive and even higher inductive types, so things like quotients or homotopy pushouts, suspensions, those kinds of things. You can derive induction principles from just the recursors of those type in a very straightforward manner that basically just follows the same 3 steps I just showed you. And this makes some nice progress on something that was previously a bit of an issue, because previously induction principles could be derived from recursors using the Aberlé-Frey-Spite encodings for impredicative encodings of inductive types. But this was done by restricting these encodings to elements satisfying certain higher categorical coherence conditions. And these conditions quickly grow in complexity and become intractable to work with the higher levels of categorical structure you're working with. This is basically an instance of the infamous coherence problem in homotopy type theory. And so the approach in terms of cohesion suffers none of these defects and easily handles examples such as the circle, for which the analogous Audi-Frey spite encoding is already quite complex. And so finally, I just want to say that these results have all been formalized in Agda. And so that means that anyone who's interested can import the code and start using it to prove parametricity theorems in Agda today at this URL. And one other thing to note is that in this talk, we mostly talked about unary parametricity, but this approach handles binary and more generally n-ary parametricity equally well. In fact, after I posted the archive version of this paper, Jason Reed started playing around with it, and he actually has a really nice formalization of k-ary parametricity for any type k with decidable equality. So this already is kind of a nice advantage of doing this internally independent type theory. You can actually push it a bit further than you normally would with external parametricity, because as far as I know, people have only ever really done that for like binary arities. And so in closing, I am hoping that this account of parametricity by cohesion or some suitable generalization can serve as a unifying framework for these and other applications of internal parametricity in dependent type theory. One thing that I'm especially interested in exploring is internal parametricity for linear programs or substructural programs, possibly in some form of linear dependent type theory. And that actually also has potential applications to some of the other approaches that have been taken to internal parametricity, because some of those have relied on various sorts of substructural properties of the interval. So that's something I'm currently looking at. But so, yeah, that's my talk. And so thank you very much.
Lots of time for questions.
Yes.
Yep, Andy?
So, my personal experience of dabbling with angle type theory.
Mm-hmm.
Right.
Yes. Yes.
Is that if you can avoid it.
Oh yeah.
For all sorts of things, but I mean, like something is, you know, like who knows whether the parents playing in anger.
Yes. Yes. Yes.
So my question is there any way of avoiding
That's
I mean, you could think of ways of saying the interval is
yes.
require.
Yes. Yeah. So I think that's definitely an interesting thing to think about, because even in this formalization I have really not used the flat modality all that much. It basically, yeah. It basically, all that it's doing is kind of showing that the sort of sub-universe of path discrete types is non-trivial, or that like it's closed under all your usual like inductive types and those sorts of things. So that potentially is something worth looking into from at least a usability perspective, if not, as you said, like a yeah.
I mean, you could, but there is just because it would make people.
Yes. 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 Thank you. Yeah. Yeah.
So you look at what about the coherence for that state theory?
Mm-hmm.
And I don't know that much about parametricity, but I've seen that some people using parametricity of semi-symmetric concepts.
Yes. Yep.
And so it's now you have a parametricity internalized in plots.
Mm-hmm.
It's used to define semi-symmetrical types inside modality theory.
That's something I am currently looking at myself. There's a bit of a still kind of like, so this formalization kind of takes you as far as like classical parametricity results for the most part. Some of the stuff about doing semi-simplicial types and things like that actually depends on some of those substructural things I was talking about in a kind of interesting way, which is one particular reason why I'm very interested in looking at combining this sort of parametricity with substructural constraints. So, yes. Yes.
Thank you for your talk.
Thank you.
Great results. A few years ago, there was a paper about cohesion, and it was about proving information flow property.
Yes.
And one of the main things that was useful there was this actual code streetness. That's all the
Yes.
data.
Yes.
So that's the shape of the code street thing is something.
Yes.
So did I miss it? Did you use it a lot?
It doesn't show up. You can add that. Fairly straightforward. Yeah. No. Yes.
I'm sure I want to use it heavily.
Yes. Yes.
Okay.
Yeah.
Anyone else?
Yeah. Anyone else?
Last question.
Yeah.
I guess it was all a lot about dimensional calculations as
Yes,
well, and all
yes.
the traditional models from also huge literature, people last later, a lot of people in the 2000s. Do we yet know how, I mean, that Cohesion paper did use essentially the same model of reflective graph,
Yes.
but did quite use parametric perspective. Can we relate that to more traditional than other models? How is the model related? Can we now combine it or have to work for back years?
That is also something I'm currently looking at. So I don't have much to say in the way of like concrete answers, but that's other than that, that is a very interesting thing to look at. So yes, and I think so far results are promising, basically. Yeah.
Other questions from the audience?
I'll give it.
Yeah.
So what's the ways that we sort of explain like parametric to like just by thinking of color?
Yes.
How does cohesion
Okay. So I'm going to say stuff that I don't want you to quote me on because I'm gonna be possibly mangling some of it. You should talk to my friend Astra about this because she knows more about that. But basically, so a different but very closely related to the reflexive graph model of cohesion is simplicial sets, which are cohesive over sets. And basically you can think of that as like sort of a category of diagrams sitting over your base category and forcing everything to be parametric / cohesive, et cetera, with respect to all those diagrams basically forces all of your naturality, functoriality, et cetera properties to hold. So that's the idea. Yeah.
Question. We have plenty of time.
Yeah.
The condition on the base category cohesion, but there was an object.
Or so I think it's so you might be talking about when you're looking at like for a Grothendieck topos to yes. Yes. So terminal object is enough to get you the flat modality. There is a notion of a cohesive site, which like if you look it up on NLab, you can see what that is off the top of my head. I think it's something like it needs to have a terminal object. It needs to, what's the word? And then there's some technical condition for that, which specializes to something relatively simple when you're looking at pre-sheaves. So.
I have a question.
Yes.
What about the cohesion doesn't hold everywhere, but maybe I have some kind of relative cohesion. You thought about that?
Yes, I haven't thought too hard about that, but now that you say that, that is also an interesting thing because there's a few instances of internal parametricity where the models aren't cohesive, including even the Kolomatskaya-Shulman one about semi-simplicial types, because that's based on semi-simplicial sets, which is not cohesive. But it is closely related to simplicial sets, which is cohesive. So that could be an interesting thing to look at when you have topos that's not cohesive, but is potentially related by some other sorts of modalities to a cohesive topos. So, yes. Yeah, which.
I have another question because we
Yeah.
still have 4 minutes. So I know there was some work in the COP universe by Marc Lasson with analyzing parametricity through plugins.
Okay.
You know?
I'm not super familiar with that.
I can
But...
send you a link.
Okay. Oh, yeah, that'd be great. Thank you.
But I think it's not quite it's not like this.
Okay.
Any other question? Yes.
I have just a general question about the examples that you gave. So,
Yes.
sequential sets are three-teams over a certain index category, and then reflective graphs in my log graph play are three-teams over
Yes.
that category that's just dropped off at
Yes.
level.
Yes.
If you drop off at n level for some finite length, do you also get something?
I believe it only works for like the chopping it off at the level that gives you reflexive graphs and simplicial sets. I don't think there's any in between level that gets you anything. Yeah.
Okay. The urgent questions. I think the next topic is remote, right? So I might want to stuff around for a little bit. Okay, so let's thank you again.